This is part 2 of second derivative analysis. This is dealing with the second derivative test. So this is a test that's used to find relative extrema. And the second derivative test basically says that if you have a critical point, if the graph is going to be concave up, which means the second derivative is positive, then it's going to be a relative minimum. If your second derivative is negative, which is concave down, then it's going to be a relative maximum. However, if your second derivative is also 0 at the critical point, then the test is inconclusive. And what you can kind of think of this graphically as is if you say you have something that's concave up, it means your second derivative is positive. That's going to create a low point in your graph. And if you have something that's concave down at a critical point, that's going to create a high point in the graph. So it's kind of backwards in the sense that if you have a positive second derivative, it's a minimum. And if you have a negative second derivative, it's concave down, it's a maximum. So let's look at an example. All right. So I want to find the relative extrema using the second derivative test. And this equation might look somewhat familiar. And I first of all have to find a critical point for a relative extrema, because that's where relative maximum, relative minimums occur. So I still have to find the first derivative. So I'm going to say g prime is equal to 3x squared minus 12x. And I have to find a critical point, so I set this equal to 0. And that's going to be set equal to 0. It's going to be 3x parentheses x minus 4. So if I solve this one, I'm going to get my critical points to be x equal to 0, x equal to 4. And what the second derivative test says, instead of doing the sign analysis over here on the side, what I can do is determine the concavity at each one of these critical points. So the second derivative test is find my second derivative, so g double prime, and this is easy because it's a power 1, I can go 6x minus 12. And I'm going to evaluate each one of these critical points into my second derivative. So I'm going to say g double prime at 0. Well, when I do that, I plug in 0, it's going to, in second derivative, it's just going to be negative 12. So my second derivative is negative. And if I have a negative second derivative, it's going to be a relative maximum. So this is a relative max at x equal to 0. And I'm now going to get my other critical point, and g double prime of 4. Well, if I plug in 4 into my second derivative, it's going to be 6 times 4, which is 24, minus 12, which is positive 12. And that's going to be a positive second derivative. And a positive second derivative means you have a relative minimum. And in order to find the location of the point, I still have to plug these critical points back into the given function. So relative maximum is going to occur at 0, and when I plug in 0 to this, it gives me 15. And if I plug in 4 into my given function, it's going to give me, I believe, negative 17. And the graph of g is the one I was just showing you guys a little while ago. So you can see that this graph is has a maximum at 0 and 15, and has a minimum at 4 and negative 17. So that kind of illustrates that if it's concave up, it's a minimum, concave down, it's a maximum. What's kind of interesting to note as well is that at the maximum, I have a decreasing derivative, and at the minimum, I have an increasing derivative. And that'll be further explained in a later video. the relationship between the first derivative and concavity, but just maybe something for you guys to think about as far as at maximums and minimums, what's the first derivative actually doing as far as increasing or decreasing. Alright, one last example for you guys to try on your own, and that's going to be, let me see if I can find it here. Use the second derivative test to find the relative extrema to this. So go ahead and find the critical points. Use the second derivative test. Give you a moment to pause it. Alright, at this point I'm going to reveal the answer, and tomorrow I will be checking for the work. So here's just what the answer is, and tomorrow I want to see that the second derivative test was applied nicely and all the notation is there and all that good stuff. And that's it for this video.